All right, step 2 is separate the variables. So for separation of variables, it's kind of like the 1D problem where we're doing homogeneous particular, but different in an important way. We're going to make a substitution. We're going to say temperature, which is a function of both x and y in reality, is separable into the following equation, which is Tx, which is a function of x, times Ty, which is a function of y. So I'm assuming, based on meeting all the criteria for separation of variables, that I can take my function, separate it into 2 separate, totally independent functions, multiply them together, and get the same answer. Right? It's a little bit tricky to think about, and actually it's something that takes a while to appreciate, like what that's saying. It's saying, if you meet these criteria, yeah, I have a totally independent function of x. You plot that out, it's just a function of x. And then I have a totally independent function of y. Plot that out, it's just a function of y. I'm going to multiply those 2 things together at any point x and y, and that gives me my solution. Right? That gives me my actual solution, Tx of y. So the special criteria that we went through give you the ability to do this. But conceptually, this is what you end up with. So we're making this assumption based on the criteria. Now we actually go through and plug this in. So let's take our PDE up here in the right-hand corner, and let's make the substitution and just kind of see what happens. So we're going to say our partial derivative to the second power of Tx. I'm going to just abbreviate these Tx and Ty. I won't carry the functional dependence along. So Tx times Ty with respect to x plus the partial Tx Ty with respect to y is equal to 0. So that's just making that substitution. Pretty straightforward. What we can do now is let's observe something. We're taking the partial here with respect to x, which means y is not functionally dependent on that at all. So with respect to this derivative in x, y can come out. Same thing goes for x in the second term. So we end up with this equation, which is Ty d squared Tx dx squared plus Tx d squared Ty dy squared equals 0. Just observing the fact that y and x are not functionally dependent on the other variable, so we can bring them out. They're constant with respect to those things. Okay, then we're making progress. Right, the goal here, this is called separation of variables, so the goal is we're trying to separate variables, maybe obviously. We're making progress, but we still have this mixed stuff in here. So what should we do next? Well, let's take the entire expression and divide it by Tx times Ty. Let's take this whole thing, divide it by Tx times Ty. And we end up with, on the left-hand side, the Ty's cancel out, so you have d squared Tx dx squared, all of that over Tx. And then you have d squared Ty dy squared, all of that over Ty equals 0. So, ta-da, we've successfully separated the variables, right? We have just a term with x, just a term with y. And they're related to each other, right? You add those things up and they have to equal 0. So, okay, that's kind of the first part of this. What we're going to do now is figure out how we're going to solve these and relate them to each other. Right? We have to now separately solve this differential equation for x and then for y and somehow relate them to each other. So this equation tells us how they relate to each other. But we have to maybe think about it for a second to see what is actually the relationship. So it's not true that this is equal to 0, and it's not true that this is equal to 0. It's true that these are equal and opposite to each other. But furthermore, if we have some function x, right, and that function only depends on x, and we have a separate function t of y, and that function only depends on y, what has to be true about these two things, right? If I pick some value of x and there's a function, right, they both have to equal a constant. They have to equal the same constant. Think about that. Make sure it makes sense, right? Both of those terms have to equal a constant in order for this equation to make any sense. So we're going to write that out as following. So we're going to say my function of x, sum f of x, is equal to that first x term, which is now an ordinary differential equation because it's just an x. So d squared tx dx squared over tx is equal to a constant. Let's call this constant lambda. But in order to require that that constant is always positive or negative, let's just make it lambda squared. So regardless of the sign of lambda itself, we know that the signality of that constant is positive, right? OK, so we know that it's lambda, but we don't actually know whether it's plus or minus lambda. So let's just out in front here, right? This is plus or minus lambda squared. OK, so the same thing's going to go for the function for y. So we have some function that's only a function of y, which is now the ordinary differential equation d squared ty dy squared over ty is equal to, now it's going to be, again, plus or minus lambda. But importantly, it's actually the opposite of whatever f of x is. So we would write it as minus or plus lambda squared. All right, the only thing we know is that they're a constant and they have to be opposite sign. So we've preserved it that way. OK, so let's see. So now we have our differential equations. I mean, you could rewrite this, bring in, let's just take that one more step so we have a clean set of equations. So let's say we'll write this as d squared tx dx squared is equal to plus or minus lambda squared times t of x, and then d squared ty dy squared is equal to minus or plus lambda squared ty. And then the question is, all right, we have to decide something about, we have to resolve this issue of is it plus or minus. And there's a rule that we're going to follow to do that. The rule is you're always going to choose plus in the direction of the homogeneous boundary condition, right? And the reason for that is, actually, the way I've written it, sorry, I'm going to make you erase one thing. Let's write it this way. All this is equal to 0. So let me restate that. So with this equation, with the way we've written it here, we're always going to pick the plus to be the homogeneous direction. Okay? If we left it the other way, it'd be minus. And why is that? Well, it turns out we're going to want, in the homogeneous direction, a solution that has a repeating function in it. And if we look back at our table of solutions to ODEs, and we have a positive coefficient on the temperature term, that's going to give us sines and cosines. And that's what we want. In the non-homogeneous direction, we want something that's not periodic. So you'll kind of see where that goes and why that ends up being true. But if you just remember, we want positive here to be in the homogeneous direction. So homogeneous direction is positive. OK, we have now two differential equations, and we can now solve these separately. Questions on this? Yeah, Rob.
So if we want the homogeneous direction to be positive, then shouldn't t of x equal minus lambda squared?
So, well, maybe. Let me look back. Let's look back at the. So let's see. if you look at the table here, I think we wanted equation 2, right? So we want the positive, like we want d squared tx plus lambda squared th.
Yeah, but shouldn't?
Yes, right. This is what I'm saying, right? Second, this way of writing it gives us the sines and cosines. Okay?